There is a storm on Saturn that does not behave like a storm. It does not die. It has been there since before we had the technology to see it. No one can explain what is keeping it alive. It is a hexagon, a nearly perfect geometric shape. When NASA's spacecraft flew past Saturn in 1981, they caught a glimpse of its edges. It took years before anyone understood what the images were showing, a weather pattern that looked engineered, and then NASA sent Cassini to look straight down into it. What they found inside was worse than the shape. So, let's go inside. This is the real image of hexagon. Glowing in infrared, spinning, unchanged from what the Voyagers had seen a quarter-century earlier. This image is extraordinary. A stunningly symmetric jet stream, roughly 30,000 kilometers across, with winds clocking in at about 500 kilometers per hour. And at the very center of that hexagon, something else. A tight, fast-spinning vortex sitting right on top of Saturn's North Pole. A polar hurricane. Except this one had an eye about 50 times larger than a typical hurricane on Earth, and wind speeds roughly double those of the strongest cyclones we have ever recorded on our own planet. Kevin Baines, a planetary scientist at NASA, described it simply. He called the North Polar Vortex the belly button of Saturn. But here's where it gets strange. Although the vortex looks like a hurricane, it is not one. Hurricanes on Earth feed on warm ocean water. They drift across the surface. They are born, they rage, and they die usually within a week or two. Saturn's polar vortex has no liquid ocean beneath it. It does not drift. It is locked to the pole. And it has the full structure of a hurricane, an eye, towering eye wall clouds, spiral arms without any of the conditions we normally associate with hurricane formation. It has the architecture, but not the engine. And the hexagon surrounding it? Baines called it one of the biggest mysteries of the dynamics of Saturn. Now, to understand why this shape is so unusual, we need to understand something. Earth's atmosphere is chaos. Beautiful, life-sustaining chaos. But chaos nonetheless. It lacks the conditions for a jet stream to settle into any kind of symmetric shape. Saturn is a different story. The gas giant has no solid surface. Its atmosphere is enormous and deep, stretching hundreds, perhaps thousands of kilometers before you reach anything resembling a boundary. Its composition is far more uniform than Earth's. Hydrogen and helium make up the overwhelming majority, with traces of methane, ammonia, and a few other compounds scattered through the mix. There are no continents, no mountain ranges, nothing to break the flow. There is apparently nothing in Saturn's atmosphere to prevent a perfectly natural, symmetric shape from forming. Given the right conditions, the right rotation rate, the atmosphere is free to organize itself into geometry. And here is the fascinating part. Scientists have actually reproduced the hexagon in a laboratory on Earth. At Oxford University, researchers used a cylindrical tank of water placed on top of a slowly rotating table. By spinning the fluid at different speeds at the center and the periphery, they created a boundary between two rotating flows moving at different rates. And at that boundary, polygonal shapes appeared. The most common shape was six-sided. But depending on the speed differential and the properties of the fluid, they also produced shapes with 3 sides, 4 sides, 5, and up to 8. Kevin Baines noted that you can get squares, octagons, and other polygons. It depends on the speed and the different properties of the fluid. The mechanism is relatively elegant. A number of stable vortices of similar size form on the slower side of the fluid boundary, and these interact with each other to space themselves out evenly around the perimeter. The presence of each vortex pushes the boundary northward at its location, and this gives rise to the polygon effect. So the hexagon is not some cosmic anomaly or alien artifact. It is fluid dynamics. It is physics obeying its own rules in an environment clean enough and large enough for those rules to produce visible geometry. But that explanation immediately raises new questions. If the mechanism is so natural, Why does Saturn only have a hexagon at the North Pole? The South Pole has a jet stream, it has a powerful vortex, but no hexagon. Hubble Space Telescope observations confirmed that the South Polar region lacks any hexagonal standing wave pattern. And Jupiter has powerful polar vortices too, but no hexagonal jet stream at either pole. So clearly, the conditions have to be very specific. The hexagon does not just appear anywhere. Fluid dynamics allows polygons to form. Something about Saturn's North Pole is special. A 2020 study from the California Institute of Technology offered one possible clue. The researchers found mathematically that a stable geometric arrangement of vortices can occur on any planet when a storm at the pole is surrounded by a ring of winds turning in the opposite direction, what scientists call anticyclonic shielding. This shielding creates a particular gradient that causes neighboring cyclones to repel each other and space themselves out, which in turn can produce polygonal patterns. But even with that framework, Saturn's hexagon remains unique. Jupiter's polar cyclone is bigger and faster than Saturn's, yet Jupiter does not produce a hexagon. The dynamics do not translate directly between the two planets, which suggests the hexagon requires a very precise combination of conditions: rotation, speed, wind shear, atmospheric depth, vortex size that only Saturn happens to provide. Other researchers have explored the role of something called barotropic instability, essentially an instability that develops in the interaction between Saturn's hexagonal jet stream and its north polar vortex. Studies suggest that the vortex at the center plays a decisive role in stabilizing the hexagonal shape. Without it, the jet stream alone would not maintain the pattern. The hexagon and the vortex, it seems, need each other. We know the shape is real. We can reproduce it in a lab. We have mathematical models that predict its formation. But we still do not fully understand why it persists so stubbornly, why it appears only at one pole on one planet, and why it has endured for as long as anyone has been able to observe it. If the hexagon guards Saturn's north, something equally monstrous guards the south. Sitting at Saturn's south pole is a vortex of enormous proportions. Its dark eye is roughly 8,000 kilometers across, about 2/3 the diameter of Earth. When Cassini swung high above it in October 2006, the images it returned were 10 times more detailed than any previous picture of this feature. What had once appeared to be a largely transparent eye now revealed a multitude of cloud structures inside. Clouds on Saturn are produced by convection warm gases rising from the planet's interior. As they reach higher, colder layers, they condense and become visible. Inside the south polar vortex, Cassini could see streams of upwelling gas creating their own smaller vortices within the larger one. At one position, a stream of rising gas had spun up an entirely separate vortex inside the eye itself. A storm within a storm within a storm. The eye wall clouds towering around the vortex's edge were extraordinary. They stood between 30 and 75 kilometers above the clouds at the center. That is 2 to 5 times the height of the tallest thunderstorms on Earth, and 2 to 5 times the height of clouds surrounding the eye of a terrestrial hurricane. The reason for this exaggerated vertical scale is Saturn's atmosphere itself. Made primarily of hydrogen and helium, it is far less dense than Earth's atmosphere at comparable pressures, which means it stretches out much further in the vertical dimension. Clouds that would be a few kilometers tall on Earth become tens of kilometers tall on Saturn. Now, here is what makes this particularly interesting. Eye wall clouds are a defining feature of hurricanes on Earth. They form where moist air flows inward across the ocean's surface, rises vertically, and releases precipitation around a central region of descending air, which is the eye. Before Cassini, eye wall clouds had never been observed on any planet other than Earth. Not even Jupiter's Great Red Spot, which is far larger than Saturn's polar storm, has an eye. It has no eye wall. It is relatively calm at the center. Images from the Galileo spacecraft confirmed that. Saturn's south polar vortex, by contrast, has the complete architecture of a hurricane, the eye. The eye wall, the spiral arms extending outward, everything. Except it is locked to the pole. It does not drift. It has no ocean beneath it, and it may have been spinning there for billions of years. This vortex is comparable to the size of Earth, with winds reaching 550 kilometers per hour. So now we have a planet with a perfect hexagonal jet stream at one pole and a permanent hurricane-like vortex at the other, neither of which should exist by the standards of what we understood about atmospheric dynamics before we actually went there and looked. But the poles are only part of the story. Because once every generation, Saturn reminds us that it is not the quiet, bland world it pretends to be. Once every generation, the whole planet wakes up. Saturn, most of the time, is quiet. Its atmosphere is usually described as bland, lacking the dramatic contrast and vivid color of Jupiter's swirling bands. The clouds are there, certainly. Ammonia ice in the upper layers, ammonium hydrosulfide below that, water clouds deeper still, but the upper haze is so thick that it obscures almost everything, giving the planet that smooth, golden, featureless appearance. And then, roughly once every 30 Earth years, something erupts. And when it does, the entire planet changes. They are called great white spots, enormous storms that break out approximately once per Saturn year, typically around the time of the Northern Hemisphere's summer solstice. The first one ever observed was recorded in 1876. Others followed in 1903, 1933, and 1960. The 1933 storm was the best observed of the early ones. But none of those observers had the technology to see what was really happening inside these eruptions. Then, in late 2010, a new great white spot appeared. And this time, Cassini was watching. The first hint came on December 5th. 2010, when Cassini's radio and plasma wave subsystem detected something unusual in the data. Soon after, amateur astronomers on Earth began spotting a bright disturbance through their own telescopes. Then Cassini's cameras locked onto it. It began as a small, brilliant white cloud in the middle latitudes of Saturn's northern hemisphere. It grew rapidly. The storm remained active for more than 7 months, generating an expanding mass of white clouds that formed a turbulent ring, spanning an area of thousands of millions of square kilometers. Eventually, it wrapped all the way around the planet at roughly 30 degrees north latitude, stretching nearly 300,000 kilometers. The storm's head actually caught up with its own tail. The Planetary Sciences Group at the University of the Basque Country analyzed images from Cassini and measured the winds at the head of the storm. In that region, the storm interacted with Saturn's circulating atmosphere and generated sustained winds, typically reaching 500 kilometers per hour, with certain zones hitting 600. No one had expected that level of violence. Enrique Garcia Melendo, the lead researcher, said the team did not expect to find such violent circulation at the storm's origin point, a symptom of a particularly intense interaction between the storm and the planet's atmosphere. The storm clouds were sitting about 40 kilometers above Saturn's ambient cloud layer. Using mathematical models, the team reproduced the storm on a computer and traced its routes. The calculations showed that the focus of the storm was deeply embedded, rooted some 300 kilometers below the visible clouds. The storm was transporting enormous quantities of water vapor from the deep interior to the highest levels of the atmosphere, forming visible clouds and releasing enormous quantities of energy. That energy interacted violently with Saturn's dominant east-west winds. But despite all that violence, the storm could not move the background atmosphere. Saturn's permanent jet streams, which blow in the same direction as the planet's lines of latitude, absorb the storm's fury without fundamentally shifting. A storm large enough to encircle an entire planet, with winds exceeding 500 kilometers per hour, and it could not budge the prevailing winds. That tells you something important about how deep and powerful Saturn's internal circulation really is. The winds we see at the surface are just the visible edge of something much larger. The 2010 superstorm did something else that had never been seen before. It dredged up material from deep inside Saturn's atmosphere and brought it to the surface. Using near-infrared measurements, Cassini's visual and infrared mapping spectrometer detected water ice in the storm clouds. This was the first time water ice had ever been detected in Saturn's atmosphere. The water originated from deep in the planet, lofted from more than 160 kilometers below the visible cloud tops by powerful updrafts. That might not sound dramatic at first, but consider what it means. The classic model of Saturn's atmosphere describes it as a layered sandwich. At the top sits an upper haze of uncertain composition that obscures almost everything beneath it. Below that, a deck of ammonia ice clouds. Further down, a layer of ammonium hydrosulfide ice, and at the bottom, a deck of water clouds. Under normal conditions, none of that layering is visible. The haze blocks everything. But the 2010 storm punched through all of it. The storm particles had an infrared color signature distinctly different from the surrounding atmosphere, which is how Cassini could identify them. The team, led by Lawrence Stromovsky of the University of Wisconsin, found that the cloud particles at the top of the Great Storm were composed of a mix of three substances: water ice, ammonia ice, and an uncertain third constituent, possibly ammonium hydrosulfide. As the water ice crystals rose through progressively colder layers of the atmosphere, they appeared to become coated with more volatile materials like a snowflake, collecting layers as it falls in reverse. Stromovsky compared it to a volcano, bringing up material from the depths and making it visible from outside the atmosphere. Kevin Baines added that the finding demonstrated that typically quiet-looking Saturn can be just as explosive as, or even more so, than typically stormy Jupiter. Water ice from the deep atmosphere does not appear to be lofted as high even on Jupiter. And the dynamics of that process turned out to be remarkably similar to convective storms on Earth, where warm air and water vapor are pushed high into the atmosphere, forming towering thunderhead clouds. Except on Saturn, those towering clouds were 10 to 20 times taller and covered a vastly larger area. Models predicted vertical winds exceeding 500 kilometers per hour for these rare giant storms. Saturn had been hiding an active water cycle far below its visible surface, and it took the most violent storm in decades to reveal it. In 2015, years after the storm had subsided, researchers using the Very Large Array Telescope studied Saturn's atmosphere at radio wavelengths and reported something remarkable. They found long-lasting signatures of all the mid-latitude giant storms from Saturn's past. They detected a mixture of equatorial storm remnants that appeared to be up to hundreds of years old. And they potentially identified an unreported older storm at high northern latitudes that no one had ever documented visually. The great white spots, it turned out, do not simply erupt and vanish. They leave scars in the atmosphere that persist for centuries. Saturn remembers its storms long after the clouds have settled. As one scientist from the Planetary Sciences Group noted, these storms on Saturn serve as a kind of test bank for the physical mechanisms underlying the generation of similar meteorological phenomena on Earth. Studying them in such an extreme and alien environment conditions that are impossible to simulate in any laboratory helps refine the models we use to understand weather and atmospheric behavior on our own planet. So what is actually down there? What lies beneath the hexagon, beneath the storms, beneath all of those layers of ammonia and water cloud? Saturn is the second largest planet in the solar system after Jupiter. It has an average radius about 9 times that of Earth. It is over 95 times more massive. And yet, despite all that bulk, it is the only planet in the solar system less dense than water, about 30% less. If you could find a bathtub large enough, Saturn would float in it. That low density is misleading. The interior is far more complex than the average number suggests. Saturn's atmosphere is made up overwhelmingly of hydrogen, about 96% by volume, with roughly 3% helium and trace amounts of methane, ammonia, hydrogen deuteride, and ethane. There are also icy volatiles mixed in: water ice, ammonia ice, and ammonium hydrosulfide. The clouds vary in composition with depth and pressure. In the upper layers, where temperatures range from about 100 to 160 Kelvin, the clouds consist of ammonia ice. Deeper down, water ice clouds begin. Intermixed between them is a band of ammonium hydrosulfide ice. And in the lowest visible layers, where pressures are much higher, there are regions of liquid water droplets mixed with ammonia in solution. It is, in a sense, an atmosphere with its own geology. Layers upon layers upon layers, each with different chemistry, different temperatures, different physics. And below all of those cloud layers, the atmosphere does not end. It simply gets denser, hotter, stranger. One of the most elusive measurements in planetary science has been Saturn's true rotation period. The visible clouds rotate at different speeds depending on latitude. Near the equator, features move fastest. Near the poles, they move more slowly. Astronomers have had to define multiple systems just to describe the rotation. The equatorial zone rotates with a period of about 10 hours and 14 minutes. Other latitudes rotate in roughly 10 hours and 38 minutes. And the interior, measured by radio emissions, appears to rotate in about 10 hours and 39 minutes. But even that internal measurement has proven tricky. When Cassini arrived in 2004, it found that the radio rotation period had shifted slightly from what the Voyagers had measured decades earlier. One explanation is that geyser activity on Enceladus, which ejects water vapor into Saturn's orbit, creates charged particles that drag on Saturn's magnetic field, subtly altering the radio signal. The planet's own moons may be interfering with our ability to measure how fast it spins. The temperature, pressure, and density inside Saturn all rise steadily as you descend toward the core. At the cloud tops, the temperature is bitterly cold, around -185 degrees Celsius under normal conditions. But deeper down, it climbs. At the core, temperatures reach roughly 11,700 degrees Celsius, hotter than the surface of the Sunday. Saturn radiates 2.5 times more energy into space than it receives from the Sunday. Something inside is generating heat. On Jupiter, the excess heat is explained by gravitational compression. The planet slowly contracts, and that process converts gravitational potential energy into thermal energy. But Saturn is less massive than Jupiter, and gravitational compression alone may not account for all the heat Saturn produces. Scientists believe an additional mechanism is at work. Deep inside Saturn, helium droplets may be separating from the surrounding hydrogen and literally raining downward through the less dense material. As those droplets descend, friction releases heat. This process, sometimes called helium rain, also explains why Saturn's outer atmosphere contains noticeably less helium than the Sunday. The helium has been slowly draining from the upper layers and sinking inward over billions of years, possibly accumulating into a helium shell surrounding the core, and then there is the diamond rain. In Saturn's upper atmosphere, enormous lightning storms, roughly 1,000 times more powerful than lightning on Earth, transform methane into soot. As that carbon-rich soot falls deeper into the atmosphere, the mounting pressure converts it first into graphite, the sheet-like form of carbon found in pencils. After about 1,000 miles of descent, the pressure crushes the graphite into diamond, solid chunks of crystalline carbon falling like hailstones through an ocean of compressed hydrogen. Those diamonds continue to fall for roughly another 30,000 kilometers. But at those extreme depths, the pressure and temperature become so hellish that even diamond cannot remain solid. It melts. Some researchers have described the result as a liquid diamond sea near the planet's core. Kevin Baines estimated that roughly 1,000 tons of diamonds are created on Saturn every year. Some may grow large enough to be called diamondbergs. Scientists have known for 3 decades that diamonds are likely stable in the colder cores of Uranus and Neptune, but Saturn and Jupiter were long thought to be too hot for solid diamond to survive. The new atmospheric models changed that picture completely. Diamonds are not forever on Saturn, they eventually melt, but they are constantly being created, falling, and recycling through the planet's interior in a process that has likely been running for billions of years. As for the core itself, scientists estimated in 2004 that it is between 9 and 22 times the mass of Earth, corresponding to a diameter of roughly 20,000 kilometers. But more recent measurements suggest a more diffuse core with a mass equal to about 17 Earths and a radius equal to about 60% of Saturn's entire radius. The core is thought to be composed of rock and metal, similar in composition to Earth but far denser, surrounded by a thick layer of liquid metallic hydrogen. That metallic hydrogen layer is critical. Just as on Jupiter, the extreme pressure deep inside Saturn squeezes hydrogen into a metallic state, a liquid that conducts electricity. The electrical currents flowing through this metallic hydrogen are what generate Saturn's magnetic field. The field is weaker than Earth's in terms of raw strength at the equator, and roughly a 20th of Jupiter's. But because of Saturn's enormous size, the planet's magnetic moment is about 580 times greater than Earth's. That magnetic field, in turn, creates a magnetosphere that deflects the solar wind and produces auroral displays at Saturn's poles. The moon Titan orbits within the outer reaches of this magnetosphere, contributing plasma from the ionized particles in its upper atmosphere, and the water vapor ejected by geysers on the moon Enceladus actually becomes electrically charged and creates drag on Saturn's magnetic field, slightly slowing its rotation. The moons are not just orbiting Saturn, they are interacting with it. By the time Cassini reached the final phase of its mission, the hexagon had changed. Between 2012 and 2016, it shifted from a mostly blue-green color to a golden haze. As Saturn moved from spring towards summer, the North Pole absorbed more and more sunlight. That solar radiation was breaking apart methane molecules in the atmosphere, which then rearranged into hydrocarbon particles, essentially smog. The same kind of photochemical process that creates haze over major cities on Earth was turning the top of Saturn's hexagon yellow. Researchers discovered that smaller haze particles filled the inside of the hexagon, while larger particles dominated outside of it, with the hexagonal jet stream itself acting as a barrier between the two populations. The hexagon was not just a wind pattern, it was a chemical boundary. In late 2012, Cassini began making orbital passes directly over Saturn's poles, providing its best views yet of the hexagonal structure. These high-resolution images revealed an astonishing variety of cloud features within the hexagon, the massive hurricane tightly centered on the North Pole. Numerous smaller vortices appearing as reddish ovals, some spinning clockwise, while the hexagon and its central hurricane spun counterclockwise. Some of those smaller features were swept along by the jet stream, as if riding on a racetrack. The biggest of these secondary vortices spanned about 3,500 kilometers, roughly twice the size of the largest hurricane ever recorded on Earth. Then came the grand finale. After 20 years in space and 294 orbits around Saturn, Cassini was running out of fuel. The mission team faced a difficult decision. They could not risk the spacecraft drifting uncontrolled and potentially contaminating moons like Enceladus or Titan worlds with conditions that might support life. So they chose a daring final operation. Beginning in April 2017, Cassini performed a series of nearly 24 passes through the narrow gap between Saturn and its innermost rings. No spacecraft had ever threaded that needle before. Each pass was a calculated risk, and each one returned data of extraordinary value. The gravity measurements from those final orbits revealed that the high-speed winds at Saturn's cloud tops, reaching up to nearly 900 miles per hour in some regions, persist far below the visible surface. They extend roughly 8,000 kilometers into the planet's interior. The hexagon is not just something painted on the cloud tops. Its roots go deep. In 2020, Harvard researchers used those gravity findings to propose a new explanation for the hexagonal shape. They suggested that a deep, supersonic jet stream is pinched on all sides by smaller cyclones and pushed upward, forming the hexagonal pattern visible at the cloud level. If correct, the hexagon we see is merely the surface expression of something far larger happening in Saturn's interior. On September 15, 2017, Cassini made its final plunge into Saturn's atmosphere. It transmitted science data to the very last moment, until the spacecraft burned apart and became part of the world it had spent 13 years studying. Linda Spilker, the Cassini project scientist at JPL, said afterward that she looked forward to whatever new discoveries remained hidden in the data. Even after 13 years in orbit around Saturn, she said, the mystery and extent of the hexagon continue to grow. So here is where we stand. We know Saturn has a nearly perfect hexagonal jet stream at its north pole, roughly 30,000 kilometers across, spinning with a period that matches the planet's internal rotation. We know it was first spotted in Voyager data from 1981 and is still there today. We know it does not shift in longitude like other clouds. We know it encircles a polar vortex with hurricane-force winds and an eye 50 times wider than anything on Earth. We know the South Pole has its own monstrous vortex, 8,000 kilometers across, with eye-wall clouds never before seen on any world other than ours. We know great white spots erupt roughly once every Saturn year, storms so powerful they can dredge water ice from more than 160 kilometers below the surface and carry it to the cloud tops. We know the planet rains diamonds. We know it radiates more heat than it receives. We know that helium may be separating from the hydrogen interior and sinking slowly like rain through fog. And we know that beneath all of it, beneath the hexagon, beneath the storms, beneath the ammonia ice and the hydrogen and the liquid metal and the diamond rain, there is a core. Dense, hot, possibly diffuse, possibly surrounded by a shell of accumulated helium. A world within a world that no spacecraft has ever reached and no instrument has ever directly observed. We have reproduced the hexagon in a laboratory tank of water. We have built mathematical models that predict its shape. We have measured its winds from orbit and traced its roots thousands of kilometers into the planet's interior. We have watched it change color with the seasons. But we still do not fully understand why it is there. Why only at the North Pole? Why it has persisted for so long when similar weather features on every other world we know of are turbulent and short-lived. Andrew Ingersoll, a Cassini imaging scientist from the California Institute of Technology, put it well. The hexagon is just a current of air, he said. And weather features that share similarities to this are notoriously turbulent and unstable. A hurricane on Earth typically lasts a week. This has been here for decades. And who knows, maybe centuries. Cassini is gone now. It burned up in the atmosphere of the planet it orbited for 13 years, but its data endures. Scientists continue to pore over it years after the mission ended, still finding new details in the images, still revising their models, still asking questions they cannot yet fully answer. And there is reason to believe we will go back. The continued exploration of Saturn remains a viable option for NASA as part of their New Frontiers program. Future missions have been proposed that would include a Saturn atmospheric entry probe, something that could descend into the clouds and directly sample the gases, measuring what no orbiter ever could. And there is Dragonfly, a mission to Titan, Saturn's largest moon, which has a thick atmosphere and hydrocarbon lakes on its surface conditions that make it one of the most intriguing worlds in the solar system for questions about chemistry and the potential for life. Saturn's moon Enceladus is another story entirely. Cassini discovered geysers erupting from its south pole, spraying jets of icy particles into orbit around Saturn. Those jets contain salt-rich particles with an ocean-like composition. In 2015, a Cassini flyby through one of those plumes found most of the ingredients needed to sustain simple life forms. Enceladus may harbor a liquid water ocean beneath its frozen crust. If we ever send a probe to taste that water, the answer to one of humanity's oldest questions might be waiting beneath the ice of a tiny moon orbiting the ringed planet. Saturn does not give up its secrets easily. It sits out there, 9.5 times farther from the sun than we are, turning slowly in the cold, wearing its rings like a crown and spinning its impossible hexagon at the top of the world. Its diamond rain falls silently through the dark interior. Its helium sinks. Its storms erupt and subside across decades we can barely observe. For now, all we can do is look at the data, run the simulations, build the next mission, and keep asking the question that Saturn has been posing since the moment we first saw that shape in the clouds. How does a planet make a hexagon? We do not know. Not completely. Not yet. And that is exactly what makes it worth studying.